Now that we know a few pre-processing and vectorization techniques and have a general sense of modeling workflow, we can apply everything we've learned so far to an NLP task. In this video, we're going to do some text classification, which is a core task in NLP and probably the most common. Specifically, we're going to look at a technique called naive Bayes. We'll also revisit accuracy as an evaluation metric, learn how it can go wrong, and alternatives we can use instead. Classification is this: given some observations such as an email or a product review, assigning that observation to a class from a finite set of classes. A few simple examples would be, given a product review, classifying it as positive or negative. Given a corpus of support tickets, classifying what they're about, whether it's billing, service change, or repair. And given a passage from a book, identifying who wrote it. When you think about how often we classify things in real life, including faces, classification scenarios in the machine world are almost just as common. And naive Bayes is a classic approach to getting that done. It's fast, simple, and still widely used today. To understand naive Bayes, we need to talk about Bayes' theorem, and to understand that, we need to revisit conditional probability. As you know, a probability is just a number between 0 and 1 representing how likely something will happen or how likely a proposition is true. Sometimes this number is based on repeated observations over a long time, or it could just represent a belief in something. If you toss a fair coin, the probability of getting heads is 1/2, and the probability of getting tails is also 1/2. And if you get heads the first time, it has no influence on whether you get heads or tails on the next toss. Coin tosses are independent events. So if we want to know the probability of getting 2 heads in a row, we multiply the probability of getting heads on the first toss by the probability of getting heads on the second toss, which gives us 1/4. Another way of looking at it is this. Let's say A is the event that we get a heads on the first toss, and B is the event of getting a heads on the second toss. And we want to know again the probability of getting 2 heads in a row. We can write this down as the probability of A times the probability of B given that A happened. In this case, since the events are independent, the probability of B given A is the same as the probability of B alone, which is 1/2. Multiplying them together, we get the same answer of 1/4. Okay, so those are independent events, but in real life, things aren't so clean and easy. Probabilities of events in our own lives often depend on the outcome of other events. The probability of your flight leaving on time is dependent on the weather. If there's a higher probability of an adverse weather condition, the probability of a flight delay increases. Let's look at an example. Say you have a deck of cards and you want to know the probability of drawing 2 king cards in a row without replacement. A is the event of drawing a king, and B is the event of drawing another king without replacing the first card. So once again, we have the probability of A and B being the probability of A times the probability of B given A. The probability of A is 4/52, but unlike our coin toss example, drawing cards without replacement are not independent events. Each draw affects the probability of the next event. In this case, since we already drew a king, the probability of drawing another king is now 3/51. So B in this case is conditioned on A, and they're dependent events. So that's the formula for conditional probability. From here, we have everything we need to derive Bayes' theorem. The probability of A and B is equal to the probability of B and A through the commutativity of conjunction. And we already know the probability of A and B, that's just the formula we've been working with. The probability of B and A then is the probability of B times the probability of A given B. We can then swap the position of the values, moving each to the opposite side, and substitute the probability of B and A with the equation for A and B, since they're equal. Finally, by dividing both sides by the probability of B, we get Bayes' theorem. And as simple as it may seem, it's pretty powerful. Let's modify the letters in the formula. Instead of A and B, let's replace it with H and D, where H is some hypothesis or belief we hold, and D is some body of data. Together, this is the probability of a hypothesis or belief being true given some observed data. Put this way, Bayes' theorem provides a way to update how strongly we hold a belief as new data becomes available. For example, you may be running some subscription service and have some initial belief about whether a customer will sign up for it. And as new data becomes available through the customer taking certain actions, that belief adjusts. Perhaps the customer signs up for a trial subscription, or they respond to a survey, open emails, or contact customer service, all of which can affect the strength of your belief over time. This probability that we're trying to calculate is called the posterior probability. Let's look at the other parts of the theorem and then walk through a spatial example. To calculate the posterior, we need to quantify the strength of our initial belief before any evidence or additional data is taken into account. This is called the prior. In addition, we need the probability of observing our data given our beliefs. This is the likelihood. Multiplying the prior and likelihood gives us the posterior, though we often then divide by the probability of the data to normalize the probability to be between 0 and 1. This is often referred to as the normalizing constant. The prior and likelihood aren't always easy to get, but in our case, fortunately, we'll be able to calculate all this from our data set. In other cases, sometimes intuition or rough estimations will be needed. Let's work through a text classification example using Bayes' theorem and use a spatial representation to further illustrate how it works. Let's say you have a corpus of 90 movie reviews. Each square here represents a single review. Further, these reviews are labeled either positive or negative. Using Bayes' theorem, we want to find out the probability of a movie review being positive given it contains the word brilliant. First, we calculate the prior. There are 90 movie reviews in total, 49 of which are positive, so that's 49 over 90. Next, we calculate the likelihood, that is, the probability of the word brilliant occurring given a positive review. Let's say we go through the corpus and we find the subset of movie reviews containing the word brilliant, and it looks like this. The word is present in both positive and negative reviews. To calculate the likelihood then, we just need to look at only the positive reviews, and among those, count how many contain the word brilliant, and divide it by the total number of positive reviews, which gives us 14 over 49. There's something important to note here. Note how our probability space changes as new conditions are involved. In this case, the condition was positive reviews, so we operated in the space of only positive reviews. Finally, our normalizing constant is the probability of a movie review containing the word brilliant. In this case, there are no conditions, so we'll operate in the whole space of reviews, and it works out to 20 movies out of 90 containing the word. And if we work it all out according to the formula, the probability of a review being positive given it contains the word brilliant is 70%. Now, given this data, we didn't need to jump through these hoops to arrive at the final probability. The point here is that if you're in a situation where you have some data regarding priors and likelihood, then you can calculate the probability of your hypothesis given some data. You can also calculate the likelihood if you have the posterior. Let's look closer at Bayes' theorem as applied to text classification. We'll see what the formula looks like and we'll go through another example. In this example, we want the probability of a certain class given a document. Specifically, we're more interested in which class is the most probable. So what we want is the class among the set of possible classes which maximizes this probability. In addition, because the document is static in our calculations and we care only about knowing which class is the most probable, we can eliminate the normalizing constant. What we're left with then is this, where C hat is the most probable class. Calculating the prior is straightforward. The probability of a certain class occurring is just the number of documents of that class divided by the total number of documents. The likelihood is the probability of a particular sequence of words given a class. So the probability of these particular words occurring in this particular order. And this is tricky. To estimate the probability of every sequence of words, we need an unrealistic amount of data. So to handle this, we make two simplifying assumptions. First, word order doesn't matter. We'll just use bag of words representations, which we're now familiar with. Second, word appearances are independent of each other given a particular class. This second assumption is where the naive in naive Bayes comes from. And it's called naive because the assumption doesn't hold up in real life. For example, the words thank and you are correlated. But for the purposes of classification, it holds up surprisingly well, as we shall see. With these two assumptions, we go from calculating the likelihood as a particular sequence of words given a class to the probability of each individual word occurring given a class. And this is much easier to calculate. This way, to get the probability for the entire document, we multiply each individual word probability together. If this doesn't make sense right now, we'll be stepping through an example soon to clarify. Now, there is one more issue here.
We'll be multiplying a lot of small probabilities together, and if a document is long enough with a diverse vocabulary, this can lead to underflow where the number is so tiny that our computers can't represent it in memory.
To deal with this, we work in log space instead. So we take the log of the prior, and for the likelihood, we take the log of each individual word probability and add them together. and this is the naive Bayes classifier. Let's clarify this further by walking through an example of how this classifier is trained. Let's say we have this corpus labeled with 2 classes, medical and not medical. 5 documents in total. First, we'll calculate the priors, that is, the probability of a class occurring. That's straightforward. The probability of a document being of a medical class is 3/5, and not medical, 2/5. So those are our priors. Next, we need to calculate the likelihood of each word given each class, and that's simply dividing the number of times the word occurs in the class by the total number of words in the class. So for example, the likelihood of the word vaccine occurring given a medical document is 1/13, because the word vaccine occurs once among the medical documents, and there are 13 words in total among all the documents in the medical class. Keep in mind that for the denominator, that isn't the size of the vocabulary, it's the total number of words in the class, including repeated words. And we do this for every word. Now, there's an issue here. When we calculate the likelihood of the word haunted given the medical class, we end up with 0/13 because the word doesn't occur in the class at all. And this is an issue because when we calculate the likelihood of a document, this is either going to make the entire probability 0 because we'll have a multiply by 0 in the chain, or if we take the log, it's going to cause an error. So if we happen to have a document that's likely medical but contains the word haunted, the classifier is going to set the probability of that class to 0. To deal with this, we add a smoothing parameter, alpha, to the numerator, which often defaults to 1. So in the event a word doesn't occur, we won't get a 0. We also add the same smoothing parameter to the denominator multiplied by the size of the vocabulary. If you recall the concept of hyperparameters from our modeling video, you can consider alpha to be a hyperparameter we can adjust. So assuming alpha is set to 1, the updated likelihood of the word haunted given the medical class is then 1/34. With that solved, we go on to do the same with each word. And that's it, our classifier is now trained. Let's say we now want to classify a new document, in this case, vaccine trial, which we'll assign to the letter S. All we need to do is plug in the prior probability of the medical class and summate it with the log likelihoods of each word in the sequence. Note how the word trial isn't in our vocabulary at all, but still gets assigned 1/34 due to the smoothing parameter. If we work it out, it results in -6.87. If we do the same for the not medical class, we end up with -7.65. We're looking for the class which maximizes the posterior probability, and so the classifier returns medical as the most probable class, and that's how it works under the hood. If we're satisfied with just knowing the most probable class, we're done. But if we need it, we can retrieve some probability measure as well. To do that, we need to reverse the log operation by raising the natural exponent to the log value. The probability of the document being medical then is 71%. Keep in mind that this is a rough measure and sort of a guide. The naive Bayes classifier is known as a decent classifier, but there's varying confidence in its ability as an estimator due to its naive assumptions. So just something to keep in mind. So that's naive Bayes training and inference. As you can see, training this model is just simple accounting and arithmetic and only takes a single pass through the dataset, which is why it's fast. Before we get to the demo, let's talk a bit more about evaluation. In the last video, we used accuracy as an example measure, and we mentioned it's not the best for classification. If our dataset happens to be balanced, like this example here, then we might be able to get away with using accuracy as a measure, but most real-world datasets aren't balanced. Let's say we have a dataset where 90% of the examples are labeled with one class, and we run an accuracy metric on our classifier, and it yields 80%, which may sound good. But running a dummy classifier, which simply returns the class it most frequently encountered during training, will score 90% accuracy, which discredits our classifier. In situations where we need to classify rare or imbalanced events, accuracy is a poor choice. Instead, we can look at something called a confusion matrix and a couple of metrics called precision and recall. For simplicity, let's say we're doing a simple binary true-false classification task. A confusion matrix would then look like this, with the rows representing the actual dataset labels and the columns representing what our model predicted. We would have correct predictions running down the diagonal from the upper left to the lower right, and it's a quick way to get a sense of how our model's doing. If we look at the first column, we can derive the precision of the model, which is the number of true positives divided by the number of true positives plus false positives. What this tells us is, out of the cases which our model flagged as positive, what percentage were actually positive? And if we look at the first row, we can derive the recall of our model, which is the number of true positives divided by the number of true positives plus false negatives. And this tells us, out of the number of positive cases in our data set, what percentage did our model flag correctly as positive. So as an example, if our model performed 100 spam classifications and had this confusion matrix, we would have a precision of 74% for positive classifications and 68% recall. And it's important to know here that we can control our model's level of precision and recall, but increasing one tends to come at the cost of decreasing another. Let's say our classifier made a number of binary classifications, and this isn't specifically naive Bayes, just any classifier. The green squares are true positives, the pink squares are true negatives, and the yellow squares are incorrect predictions, a mix of false negatives and false positives. And the model's threshold for classifying something as positive is if the probability is over 50%. Any incorrect classification on the left side of the threshold is a false negative, and any incorrect classification on the right side of the threshold is a false positive. In this case, we end up with a precision score of 77% and a recall score of 83%. Alright, let's say we increase the threshold for a positive classification to 60%. In this case, any previous false positive now on the left side of the threshold is a true negative, a pink square. In a similar vein, any green square caught on the left side of the threshold is now a false negative. With a threshold of 60%, our precision rises to 90% and our recall drops to 75%. So when our model does classify something as positive, it's now more correct. However, it's missing more of the positive examples in the dataset itself. Okay, so given there's a trade-off between precision and recall, which one should we favor? It depends on what we're trying to do and which kind of error is less costly. For something like fraud detection, we'd probably want to have greater recall. It's probably better to catch more fraud incidents at the cost of a few false positives than miss them. For something where correctness is critical, such as spam detection, precision would be more important. If something's marked as spam, we'd want high certainty that it is spam so we don't miss an important message. And finally, there's a metric called the F1 score, which is a combination of the precision and recall. Specifically, it's the harmonic mean of the two. It's nice in that you get a single metric, but it favors classifiers where the precision and recall are similar in value, which may not apply to our situation. Okay, so that's a bit of coverage on how accuracy can go wrong and alternative classification metrics we can use. With that, let's look at a demo of naive Bayes. Alright, I've opened the NLP Demystified Classification Naive Bayes Colab notebook. You'll find a link to it on the module page. Alternatively, you can open it from the notebooks directory on the course GitHub repo. As we've done with all notebooks up to this point, we need to upgrade spaCy and install the appropriate English statistical model. I've already done it, so if you haven't, please pause the video and do so now. Okay, as with our TF-IDF demo, we'll use the 20 news groups dataset again, except this time we'll download the whole dataset rather than just one topic. The dataset is already split into training and test sets for us, and by default, when we call the fetch method, it downloads the training set only, but I've explicitly set the parameter here to make it clear that we're interested only in the training set for now, so we'll download that. And what we get is a collection of about 11,000 posts. Alright, the training set contains not only the newsgroup posts, but a label, or a target in this case, for each post specifying which topic it belongs to. So we have topics ranging from atheism to motorcycles to medicine. The actual targets are numbers corresponding to each topic. So the label for the first post is 7, which corresponds to rec.autos in this case. The actual posts themselves are housed in the data attribute. And looking at the content of the post, which seems to be about cars, the label makes sense. A good idea at the beginning is to look at the overall distribution of our data. So here we're plotting the percentage of posts belonging to each topic. Since this data set is curated, it's a pretty even distribution of about 5% per topic across almost all topics. In the modeling review, we talked about splitting the dataset into train, validation, and test sets. There's already a separate test set which we'll download later. For now, let's further split the training set into train and validation sets. Given this dataset is pretty small, this isn't necessary and there are better ways of handling a dataset of this size, but we'll create a separate validation set anyway just for completeness and demonstration. scikit-learn comes with this train test split utility to do the split for us.
Here on this line, we're specifying to perform an 80-20 split of both the posts and targets. The random state parameter is there to make sure the split result is the same each time so that we can recreate the results. Alright, we now have about 9,000 examples in the training set and 2,200 in the validation set. We'll set the validation set aside for now. As we did in the vectorization notebook, we'll create a spaCy tokenizer for our TF-IDF vectorizer. In the last demo we did, we disabled a few pipeline components which we didn't need, specifically named entity recognition and the parser. For our first pass here, let's try only tokenizing and nothing else. We can look at the different components in the spaCy processing pipeline using NLP.pipe names. As we can see here, there are a number of components, all of which we don't want right now. In these situations, we can disable all the pipeline components, but an easier way when we just want tokenization is using spaCy.blank, which creates a blank pipeline with nothing but tokenization. And that's what we'll do here. Looking at NLP.pipe names again, we see that it's empty. From here, we'll create this tokenization callback, which removes punctuation, removes spaces, including new lines, and takes tokens consisting of only alphabetic characters, which will exclude things like URIs and email addresses. Next, we'll transform our posts into TF-IDF vectors. This is going to take slightly longer before simply due to a larger data size. I'm going to fast forward here, but if you're following along, you can pause the video until it's done processing on your side. Now that we have our feature vectors, we're ready to build a model. Scikit-learn comes with a multinomial naive Bayes algorithm. The term multinomial just means it's meant to deal with data that has a certain distribution and where the data is countable. Text fits that description well. So we'll instantiate the model and call fit on it, passing the feature vectors and labels. This kicks off the training under the hood, and as you can see, it's quick. Looking at the internal parameters, we see that the alpha smoothing parameter is set to a default of 1. Fit prior just means the model should learn the class priors on its own. Alright, let's evaluate our model with an F1 score. Scikit-learn has a module called metrics, which is loaded with all sorts of measures we can use. What we'll do is ask our model to make predictions on our training set and see the best it can do there, and then print the F1 score comparing the labels and the model output. Setting the average to macro just means we'll calculate metrics for each label rather than use a global count. Alright, so right off the bat, we get an F1 score of about 90%. That sounds pretty good for such a basic approach, right? There's a problem though. When we downloaded the training set, we included all the metadata such as headers and footers. The problem is that headers contain information such as subject and sometimes even the actual topic category itself. For example, if a few words are often showing up in the subject line of medical posts, our model is going to focus heavily on those words being predictive of the medical topic. And that may be fine if you expect your future inputs to have similar metadata. But what if the posts we subsequently feed to the model doesn't include that metadata? At that point, our model will fall apart. So what we need to do is re-download our training data and this time skip on the metadata, which we'll do here. And once the data is downloaded, we'll redo the train validation split. So this is what a single post looks like now. Just the message body, nothing else. Much more challenging. From here, we'll regenerate our TF-IDF vectors and retrain our model. There's less text now, so it'll go quicker, but I'll fast forward. And once again, we'll ask our model to make predictions on our training set and score the results. Alright, so the F1 score dropped by about 10% once we remove the metadata, but it isn't terrible. Let's vectorize our validation data. Note here that when I vectorize the data, I'm not calling fit transform, but transform only because we built the vocabulary dictionary during the training step, and we want to use the same dictionary on our validation set. Let's ask our model to make predictions on the validation set and check out the F1 score. Okay, so that's quite a drop in F1 score. We went from 79% on the training set to 61% on the validation set. To get a clear picture of what's going on, we can plot a confusion matrix using the metrics module. Alright, let's get a handle on how to interpret this. This is really zoomed in, so I'm going to open this in a new tab. I know the labels are kind of small, but hopefully you get an idea of what's going on. As we covered in the slides, the rows represent the actual labels, and the columns represent the predicted labels. The intensity of the color of each square represents the amount of predictions made. So what we want is a bright diagonal from the top left to the bottom right, and ideally little color elsewhere. The brighter the squares along this diagonal, the greater the number of correct predictions made. So immediately we can see that atheism is doing poorly. The majority of the articles labeled atheism are actually being classified by the model under the Christianity topic. And this makes sense given their likely vocabulary overlap. In a similar vein, we can see a lot of misclassification from religion miscellaneous, where none of the articles were classified correctly, and the majority of them are under Christianity again. This is also understandable and probably reflects where the posters are from in the world. It's the same deal with politics, Mideast, guns, and even medicine. There's also a smaller cluster of errors around the technical topics with a chunk of electronics and graphics posts being misclassified under hardware, also understandable. On the other hand, topics like hockey and cryptography do well, probably owing to their specific terminology. So a few observations. The more specific a topic, the better the results. On the other hand, topics with a lot of word overlap and softer boundaries, such as atheism versus religion versus Christianity, tend to have higher errors. Let's look at the precision and recall scores by generating a classification report offered by the metrics module. Alright, so a few additional observations here. The model has perfect precision on atheism. The few times it classified a post under atheism, it got them all right. On the other hand, the recall score is terrible because it misclassified most of the posts under Christianity. And again, the more specific a topic, the better it does. Notice how the F1 score tends to be higher when the precision and recall are closer together. It's important to keep this in mind because we may care more about one aspect over another, which may make the F1 score misleading. The values under the support column, by the way, just represent the number of samples for that class. We can ignore this warning here, which is just being raised by there being no predictions for the religion miscellaneous category. Alright, so let's see if we can do better. One potential issue we have is the sheer number of features. Our training data size is only 9,000 posts, but the vocabulary is over 50,000 words. So let's reduce the number of features by removing stop words and using the token lemma instead. Before we can do that, we need to replace our blank tokenizer with a pipeline from the English Core Web small model. We don't need the named entity tagger, nor the parser, so we'll put them in a disabled list. But since we're returning the lemma, we do need the part of speech tagger and other components. And we'll also add the additional filter of removing stop words. From there, we'll re-vectorize our training data. Now, because there's a lot more going under the hood to generate the lemma, this is going to take a few minutes. I'm going to fast forward through this, but if you're following along, feel free to pause the video until it completes on your end. By the way, there are ways to optimize the spaCy tokenizer, which you can learn about through these links here. And we'll be looking at other tokenizers as well in part 2. Okay, so once that's done, we'll take a look at how many features we have now. We reduced it by a little bit, but it's still not great. Let's retrain our classifier and see what happens. Okay, so the F1 score on the training set improved a bit. Previously, it was 79%, now it's up to 84%. Let's see what happens with the validation set, which we'll vectorize first. I'll fast forward through this as well. Okay, once that's done, we'll run our model on the validation set. Okay, by removing stop words and using lemmas, we increased our F1 score from 61% to 67% on the validation set. We'll generate another confusion matrix, which I'll open in a new window. And we see some improvement. Accuracy on atheism is now up to 31%, and the Christianity column in general has dimmed. There are fewer misclassifications now. Looking at precision and recall, we see the precision for atheism has gone down, but recall has gone up, reflecting the trade-off that's occurred. And overall accuracy has increased from 62% to 70%. That's good, but misclassification around religion miscellaneous and atheism are still large sources of errors, with secondary errors around politics and guns. Okay, so the next thing we can do is adjust the alpha smoothing parameter we covered in the slides. But rather than trying individual values manually, we can ask scikit-learn to perform a grid search for us. That is, we can supply a set of alpha values to try, and scikit-learn will train a model with each value for us. We can then see which alpha value performs best. Grid search is just an elementary technique for hyperparameter search, and there are other techniques such as random search and Bayesian optimization, which we'll briefly go over in part 2 of this course. We'll also use cross-validation. This is where scikit-learn splits the training data into a number of equal-sized groups. It then sets aside one group as the holdout set and trains the model using the rest of the data. That model is then tested on the holdout set. This is repeated until each group is used as the holdout set, and this is useful in situations where we have limited data. I encourage you to read more about it through the supplied links. Normally, when you're using cross-validation, you don't need a separate validation set, but we'll keep ours just for consistency. So the alpha values we'll try are these, ranging from 0.01 to 10. And we'll initiate a grid search with cross-validation and supply the model, the parameters to try, the scoring mechanism, and the number of groups or folds we want for the cross-validation. Training naive Bayes is fast, so despite training 5 models, it doesn't take long on this dataset. So what gets returned is an object holding a bunch of data and the best model found. We can view the best alpha value found through the best params attribute, and it's 0.01. Let's retrieve the best model found, called the estimator in this case, and use it on the validation set. Our F1 score on validation increased from 67% to 73%. If we look at the confusion matrix, we can see there are fewer errors in the religion, miscellaneous, and atheism categories, though they are still the major source of errors. But their correct prediction squares are much brighter compared to the beginning, and the diagonal overall is brighter. Looking at the classification report, we also see a jump in F1 scores and accuracy overall. Alright, so we won't improve this model further, but a few ideas to explore if you're curious. We can augment this data with posts from similar forums, and that might lead to better results just from having more data. That of course assumes the nature of the posts are similar. We can incorporate n-grams. There may be high signal bigrams and trigrams in the posts. One thing worth exploring are constraints. Your business goal may actually allow you to do things like remove certain categories or merge them, which will reduce the chances of misclassification. I don't think using the count vectorizer is going to do anything, but I threw that in there. Idea 6 with adding more stop words, we'll expand on that further in a moment, and there are other ideas as well you can try out. My view is that it'll be hard to do much better than what we have because of the vocabulary overlap between the religion-related topics and to a lesser extent the technical-related topics. We would need to capture more context to tell those posts apart, either through n-grams or more advanced techniques we'll see in part 2. For idea 6 in particular, where we can potentially add more stop words, we can use this function here to look at the top 10 words per topic and see if they have much signal. Let's take a look. So in cryptography and hockey, for example, I'd say these are pretty specific terms and relevant to the topic. On the other hand, atheism has a lot of generic words like people, think, and say. Perhaps we can remove them. Beyond that though, the word God also occurs in multiple categories of that domain. And finally, before we train our final classifier, I just want to show the dummy classifier scikit-learn has. This is a classifier which we can train and specify to use a particular strategy. For this first one, we'll have the dummy classifier simply label everything with the most frequently occurring class, which results in an accuracy of 4%. And the next one just guesses randomly and also scores around 5%. These make sense given the distribution of our data. These dummy classifiers could be useful as a sanity check. Alright, let's train our final naive Bayes classifier using the final training set, so including the validation data, and with the best alpha parameter we could find. This time we'll use scikit-learn's pipeline function. We can supply this pipeline with a series of transformation steps with a training step at the end. In this case, it's pretty simple. We want our text vectorized using TF-IDF, and those vectors should then be used to train a naive Bayes classifier. This approach makes the code cleaner and reusable, especially when you create multiple pipelines. This pipeline can also be used for predictions. Any data point passed to it using the predict method will apply all the transformations listed in order and run it through the classifier. Okay, I'll kick off the training and fast forward because vectorization will take a few minutes. Okay, we have our trained classifier. Now we'll download the 20 newsgroups test dataset. Once we have the test dataset, we can pass the data directly to a predict method, and it'll take care of both the vectorization and classifying according to the pipeline we set up. Let's look at a confusion matrix for the test set. Okay, so looking at this, we see there's still a cluster of errors around the soft miscellaneous topics, mainly around religion, politics, and guns, and also some mild errors around the overlapping technical topics, but overall it looks okay. Looking at a classification report, the overall accuracy is 69%, with most major errors again around the soft miscellaneous categories. Alright, let's make some predictions. Here I have a function which, given a classifier and some text, returns the most probable class along with its probability. The strings I'm using for testing are from specific subreddits from the same topic. So the first string is from the medicine subreddit, which our model classifies correctly with an estimation of 78%. The second one is from the space subreddit. The third is from cars. And the last is from electronics. These last two sentences are ambiguous as far as classification is concerned, and I just made them up. In this case, the classifier predicts PC.hardware with just 8%, and Christianity for the second. For situations like this, we could add additional logic to accept classifications only above a certain threshold, such as 35 or 40% certainty. If it's below that, we could do something like send it to a human or dump it if our use case allows it. But these strings can't really be classified anyway without more context. As a reminder, be mindful when using these probability estimates. As we discussed in the slides, naive Bayes is good at returning the most probable class, but the actual probability estimates should be taken with caution because of its naive assumption. If you really need probability estimates, then consider another model. Okay, so let's recap. In this video, we covered Bayes' theorem, which provides a way to update our beliefs about a hypothesis given new evidence. We looked at how Bayes' theorem can be applied to classification through the naive Bayes model, which is fast to train and update. It makes a good base model to start with, and the naive assumption holds up well. And we learned how accuracy can go wrong and alternative metrics such as precision and recall. In addition, we looked at hyperparameter search and cross-validation in the demo. In addition to naive Bayes, there are other popular non-neural classification algorithms out there, including logistic regression, support vector machines, and decision trees. Logistic regression and the advanced forms of decision trees in particular are worth learning. Logistic regression tends to hold up better in situations with less independence among the words. It's also a popular classical algorithm to start with when it comes to classification tasks in NLP, and there have been papers showing that as document length increases, logistic regression tends to outperform naive Bayes. We aren't covering logistic regression here because in part 2 we'll be covering a variety of concepts including gradient descent, learning rate, the sigmoid function, and the cross-entropy loss function, all of which are directly applicable to logistic regression. Once you have those concepts down, you'll know almost everything about logistic regression, and you'll be able to pick up the rest on your own. As a side note, algorithms such as naive Bayes are known as generative models. They model the joint probability of x and y, that given some observation, they return the class most likely to have generated that observation. Logistic regression, on the other hand, is a discriminative model, which tries to learn the decision boundaries between classes directly. That is, it tries to learn which features in the data best discriminate between the various classes. Just a side note there, because you might come across that in the literature. Okay, in the next video, we'll keep applying what we've learned so far to automatically find topics in a pile of documents.